Dans la vidéo précédente, nous avons
In a
introduit
previous
quelques
video,
rudiments
we introduced some basic cosmology notions, and we tied the notion of the redshift to the expansion factor of the universe. The challenge is now to link redshifts to distances, because they can be calculated or predicted by cosmological models. If we can measure distances, we can test cosmological models by confronting the predictions of the models to the observations and by looking at models which are best capable to predict the measured distances. We will see in this video how to measure the distances and what the significances of these distances are. We will see that there are essentially two available models for this. One is founded on what we call standard rulers, and the other on standard candles. In the case of the standard ruler, the principle is to measure how the angular size of an object varies with the redshift, if also now the physical size of the standard object. We know its distance. It's what is drawn here, where we see a galaxy with an intrinsic size, an apparent size. The intrinsic size will not change with the distance, but the measured size, the angular size of the sky, will change, and it's like this that we will be able to measure the distance. We can hold the same logic and measure the apparent luminosity of an object of which we would know also the intrinsic luminosity, i.e. the absolute magnitude. It is what is shown here, a standard candle, with a well-defined intrinsic luminosity whose apparent luminosity will diminish with the redshift and the distance. It's thanks to these standard rulers and standard candles that we can link the redshifts to the distance and make cosmological measurements. What are we searching for in cosmology? We are trying to establish a connection between redshifts and the time that passes after the Big Bang. So the time after the Big Bang is summarized in this slide. We have here the time beginning at time 0. The beginning of the time is the Big Bang, which is around here. And then time passes after the Big Bang. We arrive here, for example, at a redshift of 4, which corresponds to 1.5 billion years after the Big Bang. So time flows in this direction. At present time, we are around 13.8 billion years. And we will try to establish a connection between the redshift and time after the Big Bang, so the distance. To do that, we need more and more powerful observatories. So here we have the evolution in time of different observatories. Here's the Mount Palomar Observatory with a 5-meter telescope in diameter, which allowed us to reach redshifts on the order of 1, with cameras that had the sensitivity of the 90s. Then from space, with more and more sensitive cameras, as more and more servicing missions to the Space Telescope allowed, to replace the cameras that were used with the telescope, we were able to go even greater distances. Here, we see that we added infrared. Why? Simply because the spectrum of the galaxies we try to observe will be more and more redshifted, to the point of reaching the infrared domain. We therefore need infrared detectors if we want to observe at extremely large distances. That is the actual Space Telescope with optical and infrared detectors. And then there is the next generation Space Telescope, the James Webb Space Telescope, which will have only infrared detectors. It will be able to see extremely distant galaxies. The diameter of the James Webb Telescope is also much bigger, 3 times the actual Space Telescope diameter, which has a diameter of 2.4 meters. What we try to do in observational cosmology is to use the fundamental relation we established in the previous video between the redshift z, or actually 1 plus z, and the expansion factor of the universe, alpha t, and what we can measure, the cosmological redshift, measured by Doppler effect. That is the wavelength of an object as we would observe it, and that is the emission wavelength of a signal in the object's frame of reference that emitted the signal. The cosmological models give us the possibility to determine the distance to the objects, which will be a function of the redshift, or the expansion factor, and the cosmological parameters. These cosmological parameters will be essentially H0, but also the density of the different components of the universe. These components will include the repulsive dark energy, which is responsible for the accelerated expansion of the universe, and dark matter. Now, how to define the distances? I said that we have standard rulers and standard candles. For standard rulers, we will suppose that we have an object of which we know the intrinsic radius. And then we observe this object at a given distance, d, from us. And this object will underlie a solid angle. The object has a given radius, which underlies a certain solid angle. It is at a given distance from us, and that is of interest. And we will have a relation between these three quantities. It's simply the relation between the solid angle and the radius of the object. The solid angle will be equal to pi r squared. R is the radius of the star. And d is the distance that we are interested in. So by measuring the solid angle, if we know the intrinsic radius of the object, we get the distance we will call the angular diameter distance. dA, z, will be equal to the square root of pi r squared over w. W is an angle. This is what we call angular diameter distance. We also said that we have standard candles. If we look at what happens at the level of the standard candles, how will we define the distance? If we have a standard candle, we do not have anymore a stellar object with a well-known, well-calibrated, well-determined radius, but we have a certain luminosity, which will be the standard luminosity. We have already seen how to measure the flux of an object with a certain well-known luminosity, L. The object has an isotropic radiation at a certain distance, d, from itself, and sends us a flux diluted over a sphere like this. And the flux is simply F equal to L divided by 4 pi d squared. This allows us to define a second distance. If we measure the flux of an object, we know its intrinsic luminosity. We deduce from it the distance we call the luminosity distance, which depends on z, redshift, measured by the Doppler effect. So we will have d equal to L over 4 pi times the measured flux. This is what we call the luminosity distance. So we have two possible definitions of the distance, one based on standard rulers and the other on standard candles. So objects that have either a well-known size or a well-known luminosity. It's like this that we will define distances. So let's see how these models. We use a given cosmological model without giving the details of this model. Here, the curves that link the redshifts to the distances, in this case luminosity distances, and in this case angular diameter distances. We have two types of distances. In the case of luminosity distances, we have dl, z, equal to the square root of L over 4 pi f. If we know an object of luminosity L and place it at different redshifts, we will measure a given flux and deduce a given distance. This is the predicted distance by a certain cosmological model. We have the angular diameter distance on one side, which will be equal to pi r squared. So the intrinsic radius, which we are supposed to get by an independent method, and the solid angle which underlays the object. We see that we do not have the same relations. We do not have the same curves. We have, in fact, a relation between the different distances. We have dl, z, equals 1 plus z squared times daz. It's for this that the curves are different. They are different, but not incompatible. We just have two ways of defining distances. It's important to define how we look at distances, either with angular diameter distances or with luminosity distances. In both cases, we have to confront the correct observations. to the correct theoretical predictions. Here we have models that predict luminosities or apparent fluxes. Here we have models that predict apparent solid angles for reference objects. It's important to know what distance we are talking about. There is also something that might seem counterintuitive. In the case of luminosity distances, an object gets fainter and fainter as the redshift gets higher. Here, when the redshift goes up, the angular diameter distance to an object will get to a peak and then go down. This means in practice, the apparent diameter or apparent radius of an object in the sky, when its redshift gets higher, the apparent diameter will first go down. Omega goes down and then goes up in this part here on the curve. An object that we will put further and further will have the tendency of getting bigger and bigger in appearance. However, its apparent luminosity will continue to diminish, and the distances are linked by this equation here. Now we will concentrate on the standard candle methods to measure distances. We will link the velocity to the distances with Hubble's law, valid for small shifts up, small z. Or in other words, we will try to link the distance to a function of cosmology, z, and cosmological parameters. Here, z is measured by Doppler effect. Cosmology are the parameters of a model, and when we change these parameters, we change the prediction of these models. D is what we try to measure with standard candles. We have a very useful tool for that, the distance module micron. The difference between the apparent magnitude and the absolute magnitude of an object, which is equal to 5 times the log to the distance seconds minus 5. So the method is very simple from here on. If m is known for a standard candle, and if m is measured, then we can deduce the distance. The standard candle method is extremely simple. We use the distance modulus. We measure it by measuring the apparent magnitude of a celestial body, of which we know also the absolute magnitude, and we get the distance. There are a series of objects which we can consider as standard candles. The most famous are the Cepheid stars, and we will also see the supernovae. First, the Cepheid stars are gigantic stars that are extremely bright. So we can see them from far away, and they will be pulsating. If they pulsate, their radius varies periodically. We have the famous relation L equals 4 pi r square alpha T4. If the radius varies, the temperature also varies a little bit. But it's the luminosity in the end that will vary. There is a relation between the period and the luminosity of the Cepheid stars. If I show you this on a graph, here is what could be the absolute magnitude of a Cepheid star. The time is here, and the light curve of the Cepheid star. We have a given mean value. We have a mean m. We also have a period, and the Cepheid stars will also have a link between their absolute average magnitude and the period. So we have an average m, which is equal to a function of the period. Also, the luminosity grows with p. So m decreases with p because it's in magnitude. And the exact relation is m average in the v band is equal to minus 2.43 times the decimal logarithm of the period minus 1 minus 4.05. This means that if we measure, for example, observational points on a curve like this, I take a galaxy in which there is a Cepheid star. I regularly measure its photometry, and then I will have what I call the light curve. I will be able to measure the period and so have the absolute magnitude that I will be able to inject in the distance module. Here is again the formula of the distance module. We will be able to inject m average here in the formula of the distance modulus and get the distance. It's a relation that was first measured by Henrietta Leavitt in the years 1910 to 1920. It's not something recent, but it's only recently that we could apply this method with the Hubble Space Telescope to measure distances to galaxies to around 40 to 50 megaparsecs from us. There are some very well-known stars that are Cepheid stars. Obviously, the Cepheid star, which is the archetype of Cepheid stars. But the polar star is also a Cepheid star. The star towards which the rotation axis of the Earth points, the polar star, is a pulsating Cepheid star. As I said before, we use the Space Telescope to observe the Cepheid stars. We also need to separate the stars in the Messier 31 galaxy, in this case here, to distinguish between the Cepheid and other stars. I said that Cepheid are very bright. Here is one. If we measure the luminous flux of that Cepheid star in time, we see that from here to here, the star has grown in brightness. We measure the light curve, we measure the period, and we deduce the absolute magnitude. For the Andromeda galaxy, the measured distance is 778 plus or minus 17 kg per second. And the recession velocity measured by Doppler effect is around 301 plus or minus 7 kilometers per second. So the Andromeda galaxy flees from us at an approximate velocity of 300 kilometers per second. We know other standard candles which will be even brighter, so we will see them from even further away, which will be type 1a supernovae. I'll skip the details here on how supernovae work. There are two types. Type 1 supernovae stars. Those are white dwarfs, which are in orbit around a common gravity center with giant or supergiant stars. Matter will go from the giant to the white dwarf, and matter will accrete. After some time, we will have a sufficient critical mass for a supernova explosion. This is the type of supernova I haven't talked about in the previous videos. What we had until now were type 2 supernovae, which we call core collapse supernovae. We have seen that for massive stars, we have nuclear reactions up to the iron fusion reaction, which takes place from here on. The iron reaction being endothermic, the core of the star collapses, and we have a supernova explosion. This is what we saw in a previous chapter. Chapter 5 on stellar evolution. The supernovae of interest for us are type 1a supernovae, which are in fact white dwarfs. So binary stars, white dwarfs, around a giant. And matter will fall, attracted by the white dwarf, spiral around the white dwarf, and so accrete matter. After some time, we will reach the critical mass of the white dwarf. The critical mass is 1.44 solar mass, also called the Chandrasekhar mass. Each time the white dwarf has accreted enough matter, that is 1.44 times the mass of the Sun, we will have a supernova detonation. Since the critical mass is always the same, we will always have the same luminosity. Actually, it's the explosion peak that will always have the same luminosity. What is of interest here is what we call the light curve of the supernova, as in the Cepheid star's case. But this time on the axis, we have the time here, the luminosity here, and also the absolute magnitude that would be here. When the supernova explodes, it will grow in luminosity, reach a peak, and then go down. If we calibrate this curve, we will see that at a given moment, We have a luminosity peak that will correspond to an absolute magnitude in the V band of 19.3. So when a supernova explodes, we take some measurement points. We have a light curve. We make the adjustment by least square over the light curve. We measure the peak, and that gives us the absolute magnitude in the V band. Another time, that is what we will inject in the distance modulus to determine the distance to the supernova. Here are some supernovae examples. Here we have a spiral galaxy at a relatively short distance. We have here the distance c measured through supernovae of 15.5 plus or minus 6 megaparsec. That is already a lot further away than the Andromeda galaxy. We would not be able to see the Cepheids in a galaxy like this. The recession velocity here is much larger, 602, so exactly twice that of Andromeda. So 602 kilometers per second. And if we take a spectrum of that supernova, we will find that there is no hydrogen line. Instead, we will have silicon 2, i.e. silicon ionized once, that can be found at the wavelength 6,150 angstroms. It's these two characteristics that are the spectral signatures of type 1a supernovae. When a supernova explodes, we can do two things. We take a spectrum, we look if there is no hydrogen, and if there is silicium, and we measure the light curve to get the apparent magnitude of the supernova, which will correspond to a given absolute magnitude. So we will have the distance modulus and the distance to the galaxy where the supernova is. Here's another galaxy, NGC 3370. The distance is beginning to be a bit higher. We have a distance of around 30 megaparsec. We have here an observation taken by a ground telescope with the supernova that exploded, and an observation taken with the spatial telescope with the supernova before or after the explosion, in any case not present on the image. The recession velocity of this galaxy is even higher than the others, 1,279 kilometers per second for this one. Now, if we go even further, we'll be able to see the true usefulness of the supernovae tool. We have galaxies at a redshift of around 1. The redshift is around 1, and we have different supernovae here. We see an extremely bright one here. In fact, many times brighter than the galaxy in which the supernova is, which we barely see. We have another here, which is an interacting galaxy. Another one here, with a relatively blue supernova spectrum. And here another one. So thanks to these supernovae, we will be able to measure the distances to all these galaxies. The further we go, the better we will test the cosmological models. What will be important here, thanks to the Cepheids or supernovae, is to construct what is called a Hubble diagram. This Hubble diagram links the distance modulus to the redshift. Here is how one of these diagrams looks like. These are not observations or predictions. It's just a qualitative schematic. We will have here a redshift. Here the distance module m minus m. So for Cepheids, we measure the mean apparent magnitude, and we know, thanks to the period luminosity relation, the absolute magnitude. For a supernova, we know the absolute magnitude of the luminosity peak at the explosion. We measure the apparent magnitude of the explosion peak and obtain the distance modulus. Now we, of course, have theoretical predictions. I draw like this. Theoretical models which link the redshift to the distance modulus. Then, we have to take sufficiently precise observational points to be able to discriminate between the different cosmological models. We can already see here that the further one goes in redshift. The more one will be able to discriminate between the different models. If I take points too close to us, we will not be able to discriminate between the cosmological models, while there we can do it. Of course, it is harder to measure distant points, since we need bigger telescopes. But we also test the cosmology better. The prediction of the models, the difference between the curves, will be the cosmological parameters, so H0, but also the different energy density parameters. 70% dark energy, 25% dark matter, and 5% baryonic matter or normal matter. So the difference between these models here are the proportions of these different densities. If we manage to measure micron and Z, we can differentiate between the different cosmological models. Since the years 2000, we know that we live in a universe in accelerated expansion, so we are able to discriminate between the different curves in these Hubble diagrams. A word about what we call the distance scale. We have seen that we have different methods to measure distances. The goal is to go to high red shifts. We have high red shifts, large distances here. We are somewhere in the Milky Way. Then we can measure parallaxes in the Milky Way. We will be able to go distances of around 40 to 50 megaparsecs. We will be able to use Cepheids. And even further, we will use supernovae. We have a certain number of intercalibration zones. Let's say, for example, here, a zone where we have measured parallaxes for Cepheid stars. So we will be able to establish a period luminosity relation for Cepheids by measuring their distance with parallaxes. Then we have a zone here where we have galaxies in which we have Cepheids. From time to time, these galaxies will have a type 1a supernova. These are very rare. Each galaxy has around one type A supernova per century. So these objects are extremely rare. We know of approximately 10 at the present time. It's thanks to this that we will be able to correctly calibrate the relation between the supernova luminosity at their peak and the distance. Further away, we use only supernovae as distance indicators. We have three essential indicators: parallaxes, Cepheids, supernovae, which will be calibrated between each other in some zones where we have two different indicators available at the same time. And then, at a larger redshift, we only have access to extremely bright supernovae, allowing us to go very far in our distant measurements. We have seen how crucial it is important to measure distances in the universe. It's one of the rare methods, in fact the only one, we have at our disposition to test the cosmological parameters, the parameters of the models, which describe the relation between redshift on the one hand, measured by the Doppler effect, and the distance on the other hand. So what we predict through cosmological models. There are a given number of obstacles to this, but fortunately they are not insurmountable. What we need in practice are bigger and bigger telescopes to capture as much light as possible, and to see further and further standard candles. Standard candles which will send us less and less photons due to their distance. That is not all. We also need ultra-fine images at very high resolution, as shown here, a galaxy taken with the Hubble Space Telescope. In these images, we will be able, by zooming, to isolate interesting objects from the surrounding objects. For example, we will be able to see the image of standard Cepheid candles, a crowded stellar neighborhood. In this sense, the Hubble Space Telescope is absolutely crucial for cosmology.